Hi, welcome to the Team 4 Heat Exchanger Final Evaluation video. My name is Peter Klopp and I'm joined by my teammates Ben Lehrer and Nina Tedeschi. In this short video, we will be walking you through the design, manufacturing, and testing of our heat exchanger, which is designed to achieve the largest amount of heat transfer between two water streams in the smallest bounding box. Here is an external view of our device. On the left side, you can see the four inlets and outlets through which the hot and cold water are pumped, as well as the primary machine body. On the right side, you can see the sealing cap plate along with four elbow fittings and tubing to redirect the flow from the center of the device to the inlet and outlet fittings. Here is an internal view of the device, along with a schematic on the right side showing the basic design. Our heat exchanger is a type of spiral heat exchanger, in which heat transfer occurs between two parallel counterflowing fluid streams, which are wound together in a spiral. On the left side, you can see the machine spiral channels through which the hot and cold water flows. In our device, the hot water is first redirected to the center of the spiral and then channeled outward, exchanging heat with the cold water stream in the process. Cold water enters at the outside of the spiral and is channeled to the center, achieving counterflow.
Our heat exchanger was machined out of billet 6061 aluminum, measuring 7 inches wide by 6 inches long by 1.25 inches tall of aluminum and 3 inches overall with the adapters. The heat transfer passed through a 0.1-inch aluminum wall thickness. The shell of the heat exchanger was first CNC machined on our CNC mill, cutting the deep cavities before flipping the part over to cut the backside and the threads. We then used the bandsaw and hand drill to cut the aluminum cover plate and the cork gasket to seal the device together. We then installed the adapters. Here you can see the adapters installed and our device connected to the testing unit.
Here you can see our heat exchanger successfully working with no leaks. On average, we observed pressure drops of around 13.75 kPa and flow rates of 2 liters per minute for both, and temperature drops for 31.3 to 25.1 degrees Celsius and 13.5 to 7.1 degrees Celsius for the hot and cold water lines, respectively. To simulate our heat exchanger, we created a model based upon a paper that experimentally and analytically calculated the Nusselt number for a spiral heat exchanger. With this model, the theoretical heat transfer figure of merit F1 was calculated to be 147.8 watts. The aforementioned temperature, flow, and pressure data were then used to calculate the remaining figures of merit. Recorded measurements of our device's dry mass, dimensions, and total costs were used to calculate the following figures of merit. The actual heat exchange was 890.9 watts F1. The heat exchanger to volume ratio F2 was 418.4 kilowatts per meter cubed. Heat transfer to dry mass ratio F3 was 487.1 watts per kilogram. And heat transfer to maximum pressure drop F4 was 2.266 watts per Pascal, and the heat transfer to cost ratio F5 was 6.02 watts per US dollar.